Hello everyone, I am Ümit Alkuş. In this video, we will solve one problem in Chapter 8. A block of mass 40 kilograms goes down a rough slide inclined at 30 degrees. The coefficient of kinetic friction between the block and the slide is 0.2. A. If the block starts from rest at the top of the slide, a height 4 meters above the bottom, how fast is it traveling when it reaches the bottom? First of all, let us draw the free body diagram of the block. To begin, we choose the appropriate coordinate axis. We represent the mass by a dot. Then we draw all the forces acting on the body. First of all, we draw the gravitational force acting on the body, which is a downward force of magnitude m times g. Now, for future convenience, let us decompose it onto x and y axis. Secondly, since there is a contact between the block and the surface, the normal force acting on the body occurs like this, which is perpendicular to the surface. Finally, since there is a friction between the block and the surface, and the block goes down, then the kinetic frictional force acting on the body becomes an upward force along the slide. As the final step to draw the free body diagram, we draw the displacement vector and the acceleration vector like this. Now, before solving the problem, let us find an expression for the kinetic frictional force. Since there is no motion along the y-axis, the magnitude of n becomes m times g times cosine theta. The magnitude of the kinetic frictional force is mu k times n, where mu k is the coefficient of kinetic friction and n is the magnitude of the normal force. So we obtain mu k times m times g times cosine theta. Okay, that's all about the free body diagram. Let us solve the problem. The total energy at the top of the slide becomes U1 plus Q1, where U1 is the initial potential energy and Q1 is the initial kinetic energy. At the bottom of the slide, we have the potential energy, kinetic energy, and the thermal energy, which is equal to the absolute value of the work done by the kinetic frictional force. All these works appear as heat in the moving body and the fixed inclined plane. We take the bottom level as the reference level for the zero gravitational potential energy. The initial potential energy of the block is m times g times h, since it has a height h above the bottom. The initial kinetic energy of the block is 0, because the block starts from rest at the top of the slide. The final potential energy of the block is 0 at the bottom of the slide, which represents the zero gravitational potential energy level. The final kinetic energy of the block at the bottom of the slide is 1/2 times m times v squared. Finally, due to friction, there is a thermal energy which is calculated by the absolute value of the Fk dot T, which is work done by the frictional force, where Fk is equal to mu k times m times g times cosine theta, and d is equal to h over sine theta according to the right triangle in the figure. If we rearrange this equation, we get, from this equation, we can find an expression for the final speed as, if we substitute the corresponding numerical values into this equation, we obtain 7.1583 meters per second, which is approximately 7.16 meters per second in 3 digits. Part B. For the Earth block slide system, calculate the initial mechanical energy, the final mechanical energy, and the energy dissipated by friction. The initial mechanical energy, denoted by E sub mech 1, is the sum of the initial potential and kinetic energies of the block. the initial potential energy is m times g times h, and the initial kinetic energy is 0. Therefore, the initial mechanical energy becomes m times g times h. With the numerical values, we obtain 1568 joules, or in three significant figures 1570 joules. The final mechanical energy, which is denoted by E sub mech 2, is equal to the sum of the final potential energy and kinetic energy of the block. The final potential energy of the block is 0, and the final kinetic energy of the block at the bottom of the slide is 1/2 times m times v squared. Then the final mechanical energy has the expression 1/2 times m times v squared. Now we put the corresponding numerical values into this equation. Then we obtain 1024.8 joules, or in three significant figures it is approximately 1020 joules. The energy dissipated by friction, that is the thermal energy, can be obtained by making use of the conservation of total energy. As a result, we obtain the formula for the energy dissipated by friction as E mech 1 minus E mech 2. Now we put the corresponding numerical values into this equation. So we obtain 543.2 joules, or approximately 543 joules. This energy can be also found by using the expression which is derived earlier. This result brings us to the end of the discussion of this problem. Thank you for your attention. See you in the next video.